Okay, so I'm going to quickly introduce you to p-adic rigid analytic spaces, which is something that I use maybe in my daily research. So the idea is first to try to make a p-adic analysis version. I will explain what it is of complex manifolds, and basically the idea is to mimicry the following fact, which is a complex manifold is a gluing of open balls, so that we call Bn of C, all the elements in CTN for which the norm is smaller than 1 along holomorphic maps. So that's kind of the complex picture I start with, but then I have to first explain what's the p-adic and where does it come from, right? So the thing is that I can look at the absolute value, so the norm on C, and it equips the rational numbers, so the fractions of integers, with a topology. And I will just make one definition. I think it's the only one that I will give, and the whole thing, but that's important. Multiplicative norm is a map from a ring A to R plus, such that norms of x equals 0 if and only if x equals 0. Norms of xy equals norms of x, norms of y. This is the multiplicative part. And you also have the triangular inequality that you might have already encountered. So now the question is, what I'm claiming is that this equips Q with a multiplicative norm, right? But there are other multiplicative norms on Q, and mainly the only, let's say the only ones, it's a little loose, but, are this norm and what I call the p-adic norm for every p, which is p to the power minus valuation, p-adic valuation. So you just, for instance, if you have an integer, you just count how many times you can divide by p, it's the valuation, and you have this norm. And I can do a quick comparison between what happens for these two kind of norms. So if I make a quick table, so I have the complex norm and the p-adic norm. So here somehow 1 to the over 10 to the n goes to 0 as n tends to infinity. And here what happens is that p to the n's goes to 0 as n goes to infinity. Then somehow I can complete. There's a procedure called completion for the norm. And what you obtain is the field R, which is kind of the place where all of this sequence, so I take all infinite sums for n very big, so bigger than minus infinity of an modulo 10 to the n, with an an integer between 0 and 10.
Which is, this is kind of the decimal expansion.
It's exactly the decimal expansion, and you see that these, the truncation of this series are Cauchy. What I'm claiming is that they are Cauchy for this norm, and in the completion, the infinite sum must exist. And on the other part, you end up with QP, which is kind of the same. You have all base P expansions. So when you have an integer, for instance, you know that you can expand it in base 2, like the the base 2 representation. And so an is between 0 and p minus 1. And what I'm claiming is that, again, the truncation of this series are Cauchy for this strange norm, and that it's, so in QP, the infinite series must exist. And then the last part is take the algebraic closure, and you obtain the complex numbers, and here you obtain something I will call QP bar without more explanation.
So for the complex numbers, you just needed to add one number, right?
Yeah, and then the problem is that it's kind of infinite over QP. But maybe what I want to do is, here I have a notion of like a complex manifold, and I want to define another, like a similar notion over QP. Because it already looks like something that I can like do series on. You can already do some like analytic manifolds over R, but I think it was too twisted to explain. Okay. So I preferred to like make this parallel. Okay, so one thing you might know over the complex numbers is that if a function is locally analytic, means it can be expanded in power series around every point. If it's true around every point on the open ball, then it's true on the whole open ball. You have like a one expansion that works for the whole open ball. And the problem is that on the what I can call the unit ball of QP, so it's all the points in QP, QP bar, let's say, that have norm, p-adic norm smaller than 1. You can take QP if you're twisted by that. The problem is that it's not true. So there are locally analytic functions are not globally analytic. And so you kind of have a problem to understand what it means to glue things. You get too much analytic functions. And so the idea for that is to change a little bit your mind and to imagine that, so if I take the unit ball over C, now it's not open anymore. I can rather see it, rather than seeing it as a complex manifold directly, I can rather look at the analytic functions on this unit ball with values to C. And this is just all the power series, Cn x to the n, that converge for a value of x smaller or equal to 1.
Okay. Yeah.
And somehow a point and then a point of B1 of C, like a concrete point, can also be seen as a map from these analytic functions to C just by evaluation at x.
Okay.
And then what I can do is I can post-compose by the norm. And here what I obtain is what I call a multiplicative semi-norm, which is just the same definition that what I get before, but without the fact that it vanishes if and only if x equals 0.
Okay.
So the picture I have in mind here is that rather than seeing my closed ball, I think of it as a ring with points of the ball corresponding to multiplicative semi-norms on it. And the trick is that I will do the same for the p-adic numbers. So if I think, now B1 of QP, how would I want to think of it? I rather define it, let's say define it, as its ring of functions. So it's just a notation, but it's just, again, sum of Cn x to the n that converges for p-adic valuation of x smaller than 1. And again, I think of the points. Points are defined. Now it's defined in the sense of Huber as multiplicative semi-norms. It's not perfectly true. I'm cheating a little bit, but that's anyway. And so again, what do I get? For all x now in QP bar, that's the trick here. Here, because I already was on a algebraically closed field, I didn't need to go up. But I get the same thing, which is the norm of the evaluation at x. This is a semi-norm. So you still get your concrete points or points, but you get more interesting things. Because if you look at the ball with radius center x and radius r inside of QP bar, then what you can make for every such, you can talk about the norm infinity on this ball.
Okay.
And this also defines a multiplicative seminorm.
So it's, what is it? The superior?
It's like, it's the supremum of all the norms of evaluation of x for x in the ball. And it's really interesting because this is not multiplicative in the complex numbers. It's really a QP features.
Okay. Yeah.
Okay. And so that's the step. And the last thing, so I just wanted to say that here now you have your functions that you wanted to be globally analytic.
Yeah.
And that's the ring you started with, and you obtain some points. Maybe we could have stopped here, and then I want just to spend 1 minute talking about difficult things.
Yeah, sure.
Which is to go back in the other direction somehow, which is now I saw the closed ball as a ring with points and maybe some kind of topology. And I want to say that X complex manifold can be defined directly without input as a ringed space. So that's why it's getting more difficult. Which locally looks like B1 of C with analytic function sheaf of ring. So what I mean by that, it's a topological space. So it's topological space X. For every open, I have a ring which is somehow we'll call the continuous functions, analytic functions, sorry, from U to C. And for every inclusion of open, I have the restriction map, which is just in the other direction, which is just the restriction of continuous. Sorry, it's C everywhere. And that's kind of the ring space associated. And I'm just saying that it locally looks like, so there's an open on which it looks like the one I could have defined for B1 of C.
And this gives you the same concept of a...
It gives you the same concept of complex manifold.
But this generalizes to the p-adics.
Then it generalizes with difficulty to the p-adics.
Okay.
First, because I didn't describe all the points.
Yeah.
And also I didn't describe the topology I put on this strange number of points. So there is a strange topology.
Okay.
The ring is okay, it's the ring of analytic functions.
Yeah.
But the last thing, so that's the remark I will end up with, is that here my basic piece, so basically I'm gluing things.
Yeah.
It's the same as saying it locally looks like this.
Yeah.
My basic pieces, sorry, it's balls of any dimension. But the problem is that x squared on, let's say, B1 QP without 0 does not have an analytic inverse. In general. And it's basically because you could look at the power series development of square, right, of x, and you see that it has a problem of convergence with p-adic valuations. So it means that somehow B1 of QP over B1 of QP with the square thing is not the same as B1 of QP. So it is not possible to restrict to this basic piece. In the complex thing, if I had something that looked like the x square, then you should like deform it holomorphically back locally to a ball. And it's not true in this QP setting.
Okay.
And hence, you have more basic pieces that I would not dig into. But I just want to emphasize that there is more basic pieces.
So you glue your space not only from balls, but
from what is called Tate algebras.
Okay. Very interesting. Thank you.
Okay, I think that's all. Thanks a lot.
Thank you.